Alright guys, so today we're going to continue our chat about related rate problems. We're just going to look at a couple of other types of common related rate problems. So let's go ahead and jump in and get started. First thing I want to talk about with you guys is what similar triangles are and some interesting facts about them. So similar triangles, or actually similar shapes in general, are shapes that are basically exactly the same. It's just that one's bigger than the other one. Now, more specifically, similar shapes have all the same angles. And another aspect to these shapes is that their sides all have common ratios associated with them. So what do I mean by that? If you were to take the ratio of the height to the base on this triangle, that would have to have the same ratio as this triangle over here for its height and base. So that's some stuff from geometry that will come in handy with some of the problems we'll be looking at today. Right, so let's go ahead and take a look at an example that uses similar triangles. So a man 5 feet tall walks at a rate of 4 feet per second away from a light that is 20 feet above the ground. Find the rate at which his shadow is growing. All right, so I want you guys to pause the video here and see if you can draw a picture of this scenario. And when you unpause it, you'll see my picture. So here's my picture so far. We've got a guy who's walking away from the lamp that I have set up there. The lamp's 20 feet high, he's 5 feet tall, and he's got a shadow on the ground. Now, I'm going to draw a little bit more to this shape, okay? The reason he has a shadow is because the light is shining down on his head, projecting his shadow on the ground. And then we can also just draw a straight line here. And what we end up with, basically, by doing that is you can see that we have two right triangles here. We have this right triangle where its height is 5 and its base is S, the shadow's length, which we don't know right now. And we also have this big right triangle here, and it has a height of 20 and a base of, well, we don't know what this length is from here to here, so we'll just make something up for that. But the total length would be x plus s. Okay, so we have two triangles there in this particular scenario. Now, what I would like you guys to do is, I'm going to tell you that these two triangles are similar, all right? Which means that you can set up a, well, actually, before we get to that, let's just do our regular steps here. So that's step 1. Let's do step 2. Step 2 is to write down the given rate. Okay, so pause the video here, and when you unpause it, you'll see what the given rate is. So as the man is walking away from the lamp, basically what's changing is his distance from the lamp, right? And that's represented by the variable x. X represents how far the man is away from the lamp. So the rate of change of x with respect to t is how fast the man is moving. And so his speed is 4 feet per second. Okay, and notice the positive, because since he's walking away from the lamp, x will be getting bigger. In other words, it's increasing. Let's do step 3, where we write down the rate that we're trying to find. Pause the video here, and when you unpause it, you'll see the solution. So we're trying to find out how quickly the man's shadow length is changing. So that would be ds dt. S represents the length of the man's shadow. And so, once again, that's also going to be in feet per second. Now, step 4 is where the new part comes in. Step 4, we want to write out our formula. Now, our formula is going to be based on the fact that these two triangles, the green one and the purple one, are similar. And I told you something about the sides of similar triangles. You can make a ratio, if you can make a ratio out of one pair of sides on the big triangle, it should be equal to the ratio of the corresponding sides on the little triangle. So see if you guys can set up your formula for this particular problem. And when you're all done, you'll see the solution once you unpause it. There's our formula. If I take the height of the big triangle and put it over the base of the big triangle, I get 20 over x plus s. That looks like a 5, but that's supposed to be an s right there. And then that should be equal to the ratio of the height and the base of the small triangle, which is 5 over s. Now, I'm going to do something with this that I haven't done on any other related rate problem yet, which is I want to simplify this formula. I really don't like having it written out as fractions. I think that's very confusing. So I'm going to cross multiply first. I'm going to multiply s times 20. And then I'm going to multiply 5 times x plus s. So you're basically going to distribute the 5 into both terms there. And then I'm going to combine my like terms. I'm going to minus this 5s on both sides. And the end result will be a much cleaner looking formula, which I'm going to put here, which will be 15s equals 5x. So we did the little right triangle, similar right triangle setup, but I wanted to simplify it, which we haven't had to do with our formulas so far. The formulas we've been using in all of our examples so far have been fine just the way that they are given to us. But with this one, trust me, it would make your life a lot easier if you just simplify it like this first. All right, now we're ready for step 5, which is to find the derivative. So I'm going to let you guys go ahead and pause the video here. And when you unpause it, you will see the solution. And there's that. So if you take the derivative of this, you're left with 15, but then you need to multiply it by ds dt. And if you take the derivative of that, you're left with 5, but then you need to multiply that by dx dt because we are doing implicit differentiation. And now you guys are ready for step 6. So go ahead and pause the video here and do step 6. When you unpause the video, you'll see the solution. So in step 6, we're going to plug in 4 for the dx dt, and then we're going to solve for ds dt. And as a result, we could end up with 4/3 of a foot per second. So that's how fast the man's shadow would be changing. And so that's how similar triangles can come into help with some of these problems. Now, on your homework, they ask a question which really isn't so common, but I'll go over it now with you just so that the homework, I don't remember if I put this question in your homework or not. I used to, but if it's not, oh well. But if it is, this will be helpful. Sometimes they ask a different question. Instead of asking how quickly is the length of the man's shadow changing, they'll ask instead, how fast is the tip of his shadow moving? And the reason why that's a little bit tricky is because the man's shadow has a rate at which it's growing, right? We just talked about that. The man's shadow is growing at a certain rate. And the rate at which that shadow is growing is causing this tip of the shadow to move, right? But that's not the only thing causing the tip of the shadow to move. Another thing that's causing the tip of the shadow to move is the fact that the man himself is moving. So you have two rates. Not only is the man moving in this direction, but his shadow is growing in that direction also. So you're going to take the rate at which the shadow is growing, and you're going to add it to the man's rate at which he's walking, and that will give you the total rate at which the tip of the shadow is moving. Okay, we just found out from the last slide that the rate at which the shadow is growing is 4/3 feet per second. And we know from the given information in the problem that the man is moving at a rate of 4 feet per second. So if I put those together, that will tell me the rate at which the tip of the shadow is moving along the ground. So getting a common denominator and adding these things together would end up giving me 16/3 feet per second for the tip of the shadow. Okay, so if you have a question like that in your homework, then that'll help you. If not, then it's just a little bonus question. All right, let's go ahead and move on here to another type of question. A water tank has the shape of an inverted cone with the base radius 3 meters and height of 9 meters. If water is pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 1 meter deep. All right, so pause the video here and see if you guys can draw the picture of this scenario. And when you unpause it, you'll be able to see my picture and compare yours to mine. All right, so here is what the tank looks like. An upside down cone. The height of the cone is 9 feet, and the radius of the cone is 3 feet. Now, there's another cone in this problem, though, and that's the cone that's caused by the water that we're pouring into this thing. So as you pour water in, the water level rises higher and higher, right? And every time, no matter where you are at, you're always going to end up having a cone of water inside of your tank. Okay? Now that cone is going to have a changing radius and a changing height. So I'm going to put a little R here. It's kind of hard to see. But the radius of that cone is going to be increasing as the water level increases. And the height, which I'll represent with a little h there, the height of that little cone will also be increasing as the water is added into the tank. Okay? Now, our next step is usually to write the given rate. But what I want you guys to notice is, once again, we've got some similar triangles. I've got this big one here, and then I've got this littler one here. All right, so before we go any further, I want you guys to set up a ratio that will work based on these two factors. Pause the video here, and when you unpause it, you'll see the solution. Now, you might have set your ratio up like this, or you might have done the opposite, which is this. Now, either way, it's fine. But the way that I have it set up, just because I've done this problem a few times, I already know that the one on top is going to work out better. So let's go with the one that I have there. Okay. Now, once again, let's go ahead and simplify this. Let's cross multiply once again. And that's going to give me the following formula instead. 3h equals 9r. And we'll leave it at that for now. Okay? Now let's go ahead and continue on with our process. That little formula we have up at the top, that's going to come in handy in a minute. Let's go ahead and move on to step 2. Go ahead and pause the video here and do the regular second step of our process, and when you unpause it, you'll see the solution. So the rate that they gave us was the rate at which the volume of the water is changing. They're telling us that the water is being pumped into the tank at a rate of 2 cubic meters per minute. How did I know that was volume? Well, look at the units. They're cubic units, so that's a volume thing. Okay, and it's a positive value because we're adding water to the tank. All right, let's go ahead and move on to step 3. Why don't you guys try to identify what rate it is that we're trying to find. Pause the video, and when you unpause it, I'll show you my answer. So it's asking us to find the rate at which the water level is rising. And that's represented by our little variable here, h. That h represents the height of the water at any given point in time. So since we're wanting to find how fast h is changing, then that means we're looking for dh dt. And now h is a length. So we are using meters, as it's indicated over here, cubic meters, but when you're doing length, it's not cubic, it's just regular meters. And so this is step 3. We're looking for dh dt, and the outcome we would expect to be in meters per minute. All right, step 4. Now this one we have a formula for. See if you guys can identify the correct formula that we would use for this particular problem. Pause the video. When you unpause it, you'll see the solution. There you go. So that's the formula for the volume of a cone. Now, we have a little bit of an issue on this problem, and the issue is this. I want a formula that connects the variable v to the variable h. And I have that. There's a v in this formula, and there's also an h in this formula. But the problem is that there's also an r, and I don't want that r there. If you guys look at the top of this slide, it's titled More Than One Independent Variable. In other words, you have an extra variable in there that you don't really want in the problem, okay? It would be okay if that letter was just going to be a number and it would just go away, but r is not a number, it's a variable. It changes as the height of it changes as the water is added to the tank. The radius gets bigger and bigger. So that r is going to create a problem for us. So what do we do about that? That's the new situation that I want you guys to be prepared for on this particular problem. So let's talk about it. So since I don't want that r there anymore, that's why we did this in the very beginning. When you have an extra variable that you don't care about, you need to somehow come up with some kind of a formula that connects the variable you don't care about with the variable that you do, and then you can use that to replace the variable that you don't care about with the variable that you do care about. So that's why we did this step up here at the very beginning. So we had 3h equals 9r, right? Well, I don't want this r in my equation anymore. So I want to replace it. So to do that, I need to find out what r equals. And to do that, all you need to do is divide both sides by 9. And you end up with 3/9 h. And we can reduce that to be 1/3 h. Okay? So I'm going to be replacing the r with 1/3 h. And now my formula that I'm going to be using has a v and an h. And it doesn't have any other kinds of variables in it. We don't like these other variables. So I replaced the r with 1/3 h. So that's the main thing I wanted to teach you with this particular example. Sometimes you end up having a formula with more variables than you want. When that happens, you're typically going to have to do something to find a new equation that will relate those two variables so you can get rid of the extra variable that you don't want anymore and write it in terms of the variable you do want. Okay? That's a tricky thing, but that's that. So let's simplify this formula a little bit. Running out of space, so I'm going to go ahead and make me some space here. So if I square this and then multiply it times this, here's what I will have as a result. I will end up with 1/27 h cubed times pi. Okay, so that's the end of step 4. I found a variable that connects the two variables I care about, and anytime it has an extra variable that I don't care about, we need to replace it with something that is useful to us. All right, now we're ready to do step 5. So I'll let you guys pause the video here and move on to step 5, and when you unpause the video, you'll see the solution. So the step was to take the derivative. So the derivative of v is dv dt. And then when we take the derivative of this side, since the 1/27 and the pi, those are just constants, so they just stay the same. But what does change is we take the derivative of the h cubed. The derivative of h cubed will be 3h squared dh dt. Now if I put together all my constants, I want to multiply together 1/27 times 3 times pi. If I multiply all those together and simplify, I'm going to end up with pi over 9. And I forgot my square there. Oops. And so now I've got a simplified derivative formula containing all the variables that I want. Okay, now we're ready for step 6. So go ahead and see if you guys can do step 6. Pause the video here, and when you unpause it, you'll see the solution. All right, so here's the solution. We replaced the dv dt with what we had for that earlier, which is 2. We replaced the h with 1. And the result is this. By squaring the 1, we get this. And then by multiplying both sides by the reciprocal of pi over 9, we end up with the answer you see there. And we still have our units to include, which is feet per, no, I'm sorry, it's meters per minute. And there's our final solution. So the whole point of this problem was mainly to show you what happens when you have an extra variable that you don't want. And the answer is you need to find another equation that can relate the variable you don't want to a variable that you do want and solve that variable for the one you don't want so you can replace it. Okay? Let's go ahead and move on to talking about right triangles, our last problem of the day, using SOH-CAH-TOA. Anytime you're dealing with a problem that's pertaining to the angles of a right triangle, you're probably going to end up using this. As you guys might recall, SOH-CAH-TOA stands for opposite over hypotenuse is sine, adjacent over hypotenuse is cosine, and tangent is opposite over adjacent. Okay? So what does all that mean? Well, let's draw some triangles. On all these triangles, I'm going to specify this angle here as my reference angle. By reference angle, I mean that's my starting point. Now the side that's across from that is what we call the opposite side, so I'm going to put an O. And we all know what a hypotenuse is. And the side that's next to it is called the adjacent side. Okay? So I could label this as an A here, but I'm not going to. I'll tell you why in a minute. Over here, I'm going to label it, though, as an A, and I'll call this my H. And on this one over here, I'm going to call this opposite and adjacent. But all three of these triangles have an opposite, an adjacent, and a hypotenuse. But for each of these three, I'm picking a different pair to include. Okay? The reason for that is because sine is the one that is opposite and hypotenuse. So if you ever have a triangle where you are interested in the opposite and the hypotenuse, the equation you're going to set up is going to look like this. The angle goes there, and then it's opposite over hypotenuse. If you ever have a right triangle where you're dealing with the adjacent and the hypotenuse, that's cosine. It's adjacent over hypotenuse. And then finally, if you're ever dealing with a triangle where you're dealing with tangents, it's going to be opposite over adjacent. And a way to remember that is with this little mnemonic up here. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and so on. Okay? Now just so you guys know, it might come in handy also for you to know that cosecant is the opposite or the reciprocal of sine, right? Now this is a little bit less important, but I'll write it small here. So if you ever want to find a cosecant, which usually we won't, but it can come in handy, that's the reciprocal of sine, whereas secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Okay, but the main ones we're going to be focusing on are sine, cosine, and tangent. All right, so that's a little review from trigonometry or basic geometry that will come in handy for our next question. And we're going to be using those anytime we're dealing with a situation where it's asking about something pertaining to the angles of a right triangle. So let's take a look at an example that is like that. A 10-foot ladder is sliding down a wall, that sounds familiar, at a constant rate of 2 feet per second. How fast is the angle of the base of the ladder and the ground changing when the base of the ladder is 6 feet away from the wall? All right, so I have a wall, and I have a ladder leaning up against that wall. They tell me that the ladder is 10 feet long. We can assume that the wall is perpendicular to the ground, making a 90-degree angle. And we have a couple things that we're interested in. The story problem talked about the height of the triangle. It talked about the base of this triangle. And it's also asking us about something that hasn't been asked yet about right triangles for us, and that is the angle that the ladder is making with the ground. And so when we have this kind of a situation, we want to be using a SOH-CAH-TOA. All right? But there's our picture. All right. Let's go ahead and do step 2. So for step 2, we want to identify our given rate. The given rate is saying how fast the thing is sliding down the wall. Now you guys will notice I'm not asking you to pause the video this time because after this problem, I'm going to let you guys do one that's similar to it completely on your own. Okay? So for now, just follow along with me. So if it's sliding down the wall, which variable does that tell me the rate of? That would tell me the rate of h if it's sliding down the wall. And so it's dh dt is the rate that they've given me. And since h is decreasing as the ladder slides down the wall, the h gets smaller and smaller, right? We're going to say that that's a negative 2 feet per second. Now I want to identify the rate that's given. I'm sorry, the rate that I'm trying to find. The rate that they're asking me to find is how fast is the angle changing. In other words, what's happening to this? Well, that would be d theta dt. Now in calculus, we always measure angles in terms of radians. So the units will be radians per second. Radians per second. All right, number 4. Formula. So here's where it's going to get interesting and different from what we're used to, because now we're dealing with a new kind of formula. Since it's asking about the angles of the triangle, then we are going to be concerning ourselves with SOH-CAH-TOA. All right. Well, I know that my formula has to have the variable h in it. And it also has to have a theta. Now, all of the trig ratios that we picked on the last, that I wrote out for in the last page have a theta. So that's not going to really be something we need to worry ourselves about. But they don't all have this side involved. Now, what is this side? Now, I know I put h here, but that h represents height. Okay, I don't want you to think that means hypotenuse because it doesn't. That means height. The hypotenuse is 10. This side over here, the height, is actually the opposite side. It's the O. So I want a trig ratio that has opposite, and you also want to pick one that has the number in it, 10. Okay, so you want to use one that actually has a constant number in it. You could use the B, but it will actually add an extra variable in that we don't care about, and we talked about that in the last problem, and we saw how much trouble that creates. So instead of putting a new variable in that's also changing, let's pick the number. So how do you know which sides to pick again? Well, you have to pick the side that has the variable you want, and then the other side you pick should be the one with just a number. Okay, so that would be opposite and hypotenuse. So which trig ratio was opposite and hypotenuse? Well, that was sine. Sine is opposite over hypotenuse. All right, so there's my formula. Now, just so you guys know, it might help if you rewrite your trig ratio like this. You don't have to, but I find that students understand it better, whereas instead of saying h over 10, if I have them write 1/10 h. That, if you rewrite it like that, it makes the next step a little bit easier. All right, so go ahead and let's do step 5 now. Step 5 is to find the derivative of that formula. So I want to find the derivative of sine theta equals 1/10 h with respect to t. So if I take the derivative of sine, that's going to be cosine. But since we're taking the derivative of something with a theta, but we're doing it with respect to t, I need to multiply it by a d theta dt. Now I'm going to take the derivative of this. The derivative of that would give me 1/10, but we're going to multiply it by the dh dt because, once again, we're doing implicit differentiation. All right, so that's the end of step 5. Now I'm ready for step 6. Step 6 gets a little bit interesting as well. So let's take a look at step 6. So for step 6, we plug in stuff that we know. The only thing I know right now, right off the bat, is dh dt is negative 2 feet. So I'm going to plug that in right here. The other side, we know that we don't have this yet because that's what we're trying to find. So I'm going to put d theta dt. But this next part is a little tricky. I need to figure out what is cosine of theta. Well, believe it or not, we actually can find that, interestingly, in a fairly simple way. So in the word problem, which I have erased, let me get rid of all my stuff and I'll reread it to you. They tell us an extra piece of information, like they usually do. They tell us that we want to find this rate at the time when the base of the ladder is 6 feet away from the wall. So if I go back to our picture here, where does that 6 go on my picture? That 6 would be the value of b. That's the distance of the ladder's base away from the wall. Now, if I know that, then I actually already know cosine of theta. Cosine of theta is adjacent over hypotenuse, right? What is my adjacent side? 6. What is my hypotenuse? 10. So cosine, as adjacent over hypotenuse, is 6 over 10. All right, let's go ahead and solve the rest of this then. I can reduce the 6/10 to be 3/5. And if I multiply these together and reduce, I'm going to end up with negative 1/5. And to solve the rest of it, I'm going to multiply both sides by the reciprocal. And I end up with my final answer here of d theta dt is equal to, the 5's cancel, leave me with negative 1/3 radians per second. And we would expect the angle to be decreasing as the ladder slides down the wall, right? So it makes sense that the answer is negative. All right, so that's an example of how you can use trig functions to solve a problem that's concerned with the angles of a right triangle. A couple of tricky parts in the problem are making sure that you pick the correct formula, rewriting your formula so that it's like that instead of like that, and then finally turning the trig ratio here into a number here. All right, so quite a few interesting little things to remember, but those are the top 3: formula, rewrite, trig ratios. All right, so I'm going to go ahead and change the slide and let you guys try one. I've already done step 1 for you on this problem, and I've labeled the picture for the most part. The only thing I haven't labeled, which I guess I could do now, is I haven't labeled the hypotenuse of this triangle yet. So I guess I'll call it H for the heck of it. We'll call it big H, so we don't think of it as height, but we think of it as hypotenuse. All right, so go ahead and read the problem. I've already done step 1 for you. After that, go ahead and do the rest of the steps and see if you guys can get the solution. When you unpause the video, you'll see the whole thing worked out. All right, guys, so here's the final answer here that I'll box it up in green down here at the bottom. You should have gotten 6/25 radians per second. So your given rate is dy dt, which is 20 feet per second. That's how fast the rocket's going up. We have the rate that we want is how fast the angle of elevation is changing. That's d theta dt. Now, since I want my formula to have a y in it, and I also want to include the side that has the number in it, that would be the opposite side and the adjacent side, and the trig ratio that does opposite and adjacent is tangent. And as you guys know, I like to rewrite it like this, where instead of having y over 30, I do 1/30 y. And then I take the derivative of that expression, which you'll see here. The derivative of tangent is secant squared theta. Don't forget your d theta dt. And the derivative of 1/30 y is 1/30. Don't forget your dy dt. Next, we go ahead and move on into step 6, where we're going to replace the dy dt with 20. And then we got to find out what secant squared is. Now, secant is the reciprocal of cosine, and cosine is hypotenuse over adjacent. So we need to know what our hypotenuse and what our adjacent is. They told us this is 30, and in the word problem they told us that this is 40 at the point in time that we're interested in. So if we use Pythagorean's theorem, you can find the hypotenuse. So the hypotenuse would be 50. So secant is h over a, which would be 50 over 30, hypotenuse over adjacent. If you go through and solve this equation now, you would end up getting 6/25. Okay? And so that is how you'll use trigonometric ratios to solve a related rate question pertaining to the angles of a right triangle. And that concludes our lesson and our last type of related rate question that we'll be looking at. All right, guys, till next time, see you then.